what we're going to be covering tonight is looking at logic, truth tables, Boolean algebra. There are 5 distinct areas that I want to actually cover in this time. Okay? Hopefully by the end of it, we're going to be covering all those topics. The first thing I want to have a look at is truth and truth tables. And what I'm going to do is introduce you to 5, 6, maybe more sentences than that, but these sentences here, which you may want to note down as I'm going through them. Each sentence is structured in a way that it deals with a logical argument. And one of the interesting sides of this is that the logic we apply in computing can, in certain ways, be applied to logic, linguistic logic. There's a branch of mathematics called predicate calculus that takes on the concept of treating sentences in logical forms. What we're going to do is use these sentences here just to get our heads around what exactly we mean by logic. Let's look at the first one. The sentence here is basically declaring that we need one of 2 objects to remain dry whilst walking in the rain. I know it doesn't say walking in the rain, but I'm going to assume that you don't just get wet by walking down the road. Okay? So, in this case, you need either a hooded coat or an umbrella. The sentence is implying that we need one or the other or both. This is a truth table. Most of you have probably seen these before. Some of you, this may be brand new too. The idea is the 0 represents a false. It does not exist. The 1 is it exists. So if we have a look at that truth table, we can see that, for example, if we don't have a hood and we don't get an umbrella, then we will not remain dry outside in the rain. But if we have an umbrella, we will. If we have a hood, we will. And if we go really over the top and have a hood and an umbrella, then we're going to be dry. No more dry than we were before, but we will be dry. The key term here is the or. The or statement actually defines the fact that we have any condition that will allow us to have a true. And that's how the truth table is read. That's an or truth table. Entrance requirements for computing AS. You all had these when you came here to this college. These slightly differently. In this case, we've got this truth table. In this case, it doesn't actually matter if you've got 5 GCSEs, and it doesn't matter if you've got the maths at B. It matters that you have both at the same time. If you don't have both, then you don't get into computing AS. The only way you can get into computing AS here is 5 GCSEs with a maths at B. The key term in the sentence there is the and. We know it in English is a joining word. It joins 2 parts together, and it means exactly what it describes, this and that. All conditions must be true for us to have a truth as output. The bane of most mothers' lives. You go into a shop and your kid wants a cake or a sandwich, and they want both. They want an and situation. Your mother wants you to have an or situation, and you're quite happy with an or situation because an or situation allows you to have both as well. But in this case, you're being told that you can't have both. What you can have is that situation. You can either have nothing at all, and you'll end up with nothing. But you can have a sandwich and eat something. You can have a cake and eat something. But you can't have a cake and a sandwich and eat those both. Because that's not allowed. That's like an or statement, but we've ruled this out. We have actually stated that there is an exclusivity here, that we are exclusively saying that you can have this one or this one. It's called an exclusive or. It's worth noting down, X or is an exclusive or, and what it means is where only one condition can be true. Now, aside from the fact that I think this is a little bit of a weird statement because I particularly like hot dogs with mustard, but I did come across this sentence in a logic book, which says something about logicians and everything else. But I like neither hot dogs nor mustard, is a declaration that actually I don't like either of these. I don't care if you give me a hot dog. I don't care if you give me mustard. I don't care if you give me a hot dog with mustard. None of those are going to be liked by me. The only situation where I'm going to like the food is if it does not contain hot dog and it does not contain mustard. And therefore, I'm actually looking at not having those two items. If you have a look at that, you'll notice it's the exact opposite to an OR. An OR would give us ones where these zeros are and a 0 where this 1 is. This is called a NOR. NOR. Sorry, I'm just sidelining there slightly. NOR. And basically it means a not or, where no condition can be true. It's a not or not, or. I could do that all day long. It's not an or. We need to look at nots in a moment. We will surely perish if we have no food. Seems a strange one to have. Food and water. Now, before any of you who do English start sitting there going, I didn't know NAND existed. And some of you think I might have a throwback to 1843 or something. No comment about age. That's not the traditional English word. Okay? It never has been. It isn't. It never will be a traditional English word. I've used it in this sentence to give you a sense of what a NAND is. And the truth table looks like that. Quite simply, in this case, it's the inverse of an AND gate. An AND table. The AND gave us zeros here, wanted both these conditions to be true. In this case, we're saying, no, you will perish if you have no food or drink. You will perish if you only have drink, and you will perish if you only have food. The only condition in which you will not perish is if you actually have both food and drink. It's the inverse of an AND gate. NAND with the N standing for not, which we haven't looked at yet. NAND is where all conditions must not be true. And here's the not. The first part of this sentence, I like dancing, is a declaration. If someone comes up to you and says, I like dancing, then your assumption is that they like going along to a room, waving their arms and their legs around. Oh God, that's going on. To music, hopefully. I wasn't doing to music, that's not called dancing. So, if you like dancing, I say, I like dancing, I like to go to a room, listen to music and move my arms and legs around at the same moment in time, in some form of pattern. The declaration at the end, not, instantly inverts that. Instantly tells you that that previous statement has been turned upside down. And that's what a not does. It's a very, very simple system. It takes whatever is being given and converts it straight the way upside down. And if you think back to what we had before with a not, with a nor and the NAND, that's exactly what that's doing. It's taking an and it's turning the result upside down, inverting it. A not simply inverses or inverses the condition. Hopefully that's all makes sense. Okay. Truth tables and symbols. We have two types of symbols you've got to worry about. Circuit symbols and mathematical symbols. And you're going to look at both of those. An AND looks like a D. That's the easy one to remember. A straightforward D with two inputs and one output. Notice these are the inputs on the left, the outputs on the right. Two inputs, one output. Be aware that in the real world of electronics, you can actually have ANDs with more than two inputs. But for everything you're concerned about, you will only have two inputs. So everything I'm going to be talking about will be related to two inputs. If you add more, it just simply extrapolates everything a bit further. An OR is simply an AND, but the back end, the input side is curved. Notice that the NAND is simply an AND with a circle at the front. The circle at the front means not. That's that inverter. I said to you, look at the AND gate and simply, the AND numbers. Imagine the output, and all we did for the NAND was take what was coming out of here and just completely turn the ones into zeros and the zeros into ones. And that's what this circle means. Same thing here. There's the nor. There's the exclusive or, and it's got a double edge at the back. This one here is the XNOR. That's actually a NOR, XOR, but it seems to be difficult to say NIXOR, so we actually end up saying XNOR. So the AND gate's really straightforward. We need both of the two inputs to be on for the output to show on. There's the mathematical symbol. I've used a big dot there, but generally a full stop it will suffice. That's the OR. As you can see, as long as we have something being inputted, a 1 somewhere, we'll end up with a 1 coming out. That's A and not A. Notice the line above the A. That tells you it's not A, the inverse. So whatever A is, not A will be the exact opposite. NAND. That's like the AND, but actually the result's now been knotted. Turned around. That's what that circle does. This is a NOR. The NOR is nothing more than the OR, 0, 1, 1, 1, but actually reversed, inverted by this circle. That does beg the question. Have a look at the knot. It's a triangle with a 0, an O in the front. The triangle tells you it's a knot. The circle tells you it's a knot. In a way, the diagram's telling you it's a not knot. Well, a not knot is not a knot. It's not a not knot, but it is a knot. So just be aware of that. Weird. It's the way they did it. We never used to draw a circle in the front. Now they insist on it. That's fine. They can do. They have the power to do so. XOR, exclusive OR, as we said, does not accept both inputs. It will only accept two of them. One input being 1 at any one stage. If they have more than one input coming in, it will give no output. And an XNOR is nothing more than the XOR completely reversed. Completely knotted. Okay, how complex can these things get? There's a circle made up of 3 types of what they're called gates, logic gates. The top one is an OR gate with a not at the front, so this is a NOR gate. A NAND, but not with a not, so it's an AND. It's like, I did that deliberately. It's an AND, okay? And that's an OR. We've got 3 inputs, and that's important to remember the 3 inputs. I have also given 2 letters here, part of the process. That allows me to put this table up and actually have a look and use those to identify the processes. I know, for example, that A and B are being ORed here, but then knotted. So A and B are actually being used to generate D. B and C are being ANDed, so where B and C are 1 together, they will produce a 1 at E. That only happens there. And the outputs of these 2 are used as inputs here. This is an OR gate, so those 2 are being used to produce this. Since it's an OR gate, all we're looking for is 1s. So there, there, and there. Everything else is 0. So they can get quite complex, and what actually helps when dealing with these kind of questions is to recognise that you can put letters in as part of the process to help you to identify what's going on, then try to tackle the whole thing as one go. Okay, next topic. Seems like we've kind of jumped straight from truth tables, and that's fine. We're never coming back there again, but actually these all link in. De Morgan was a guy from the 1800s who was a mathematician and a logician. If you remember your history, you'll know that there were no computers in the 1800s, or there were, but they were human beings who did maths. They computed things. De Morgan came up with a set of logical laws, and logic at this time seemed to have no purpose. It's a bit like the next set of laws when Boolean came up, and people went, what's the point? Nowadays, De Morgan's law plays a significant part in what we're looking at doing. De Morgan's law has 2 rules. If I have input P and input Q, and I not those, that is the same as taking P, not P, and ORing it with not Q. Fun, that one. The truth table for the first one looks like this. Here I've got P and Q, I've ANDed them together, and then I've knotted the results. All I've done is simply taken the zeros and ones and inverse them to get the result. And there's not P ORed with not Q. So in this case I've taken P and Q, I've knotted P, knotted Q, and then ORed the result of those. You'll notice I get the same result. And that means they are one and the same. Simple, easy rule. Rule number 2 is actually the inverse, in many ways, of rule number 1. In that, rather than P and Q, we've got P or Q knotted. Is the same as not P and not Q. Again, let's have a look at the same thing. We don't end up with the same input because they're not the same process. But we will get the same output, in each case we get the same output for both of these, so those two statements are true. I suppose one of the questions I would have is, my God, do I have to remember De Morgan's law when I walk into the exam? And the answer is, probably not. All you need to know, oh, I forgot that one. Let me deal with that one in a second. What you need to know is that there is a way of applying De Morgan's law when we need to. The next slide, I wanted to clarify something. You may or may not be aware, and in your booklet you've got a photograph of something called an integrated circuit or an IC. That is a chip that goes inside a computer. This is a diagrammatical approach that looks relatively similar to the chip. And you'll notice that what we've got here is inside these chips are 4 of each of the types of gates. These are the 4000 series chips. So this is the 4001, 11, so on and so forth. This is the OR, the NOR chip. And there's an OR symbol with the NOT side there, the NAND, and so on. You'll notice that there are 4 gates per chip. So when you hear some people talk about chips, they don't necessarily mean fish and chips. They do mean these kind of integrated circuits or ICs. It's important to remember with the 4000 series there are 4 gates of the same type on each chip. Why is it important to remember that? Well, because De Morgan's law helps us to solve this kind of problem by using this kind of chip. Let's have a look. Oh, that came up. Okay, where are these simple steps with De Morgan? Number 1, change the logical connector. That's the first thing you do with De Morgan's. What I mean by that, I mean turn the OR into AND or the AND into OR. That's all I mean. The first part of De Morgan is simply take the operator, the connector, and swap it with its alternative. OR becomes AND, or AND becomes OR. That's step 1. Step number 2 is change the logical state of each variable. If you have a not A, you turn it into A. If you have an A, you turn it into not A. And last but not least, to finish off and complete De Morgan's laws, you simply change the logical state of the entire expression. So if you have an expression, it becomes not expression. And if you've got a not expression, it becomes an expression. That might seem a little bit confusing. Three very simple laws. Change the operator, the connection, change the individual variable, then change the whole expression. What we need Here's an example. An example. This was actually an exam question that said, it's a little bit more than this. It actually said, show how the following can be reduced to 4 NAND gates using one of the NAND gates as a NOT. But that's enough with that to tell us the kind of thing we're looking at. This is a standard exam question. The first thing I want to do, you would not do in the exam, but I want to give you an idea of how De Morgan's laws helps. That's the circuit diagram. Each of the inputs, remember this side of the inputs, we've got A, B, C and D. Each of these inputs, the first thing that's happening to them is they're being knotted. So I'm knotting them here. C and D are being ORed here. So C and D are being ORed here. They're also being ORed here because they're being ORed there. I've got A and B. A, not A, is being ANDed with the result of ORing C and D, inverted. And I'm doing the same thing with B. And the final thing I'm doing is ORing those two together to get this result at the end. Also note I've used the letter Q as the output. That's a traditional way of presenting it. Okay? I have added E, F, G and H for the same reasons I did in the other one, because I want to show you a process. Don't need to do that in the exam, but it's worth it when you're practicing. Draw out the circuit, try to work out the logic of it, see what happens when you deploy De Morgan's. Don't do the next thing in the exam. That. Because that will take up probably most of the exam. That's the truth table. For that. What I've done here is taken and worked out all of the potential possibilities for all the inputs. The very next thing I've done is knotted all of those to draw that across. E and F are the same thing. If you recognise that I was simply, in this case, ORing C and D, in both cases, then E and F are the same thing. They're simply ORing these. G then is the combination between E, F and A being ANDed, and H is simply the ANDing between B and E or F. And finally I'm ORing those, just checking, yeah, I'm ORing those here. And this is the part to look at. Because whatever we do with De Morgan's theorem, or De Morgan's law, we need to ensure that what we end up at the end is identical. Not slightly, a slight variation. We cannot accept a 1 where there's a 0, or a 0 where there's a 1 in our new model. So that's what we're looking at. 3 1s are 0, 3 1s are 0, 3 1s are 0. You may have thought there's a pattern, and then when you come to the end you realise they're all zeros. So up until this point, we could have quite easily said that this was actually simply, those sets of 4s were very similar to a NAND. And then it blows it out of the water with the last one. Okay, so let's have a look at the examples. That's the original equation. I'm going to give you some time, if you haven't written that down, just to note this down, because I'm going to walk you through this anyway. Show how the following can be reduced to 4 NAND gates. Then we're given that one. And we can notice the first thing that's wrong with this is that we've got a mixture of ORs and ANDs as the connectives. And what we want is the same connective even. The collective is Star Trek, I think. Anyway. So the first stage is to have a look at this and decide what we're going to work on. Just like maths, this is simply a branch of mathematics. Remember when De Morgan worked on this, there were no computers. This is not a computer thing, this is a maths thing. And the rule of mathematics is you deal with what's in the brackets first. Now in this case, I noticed that I've got C or D, sorry, not C or not D, not C or not D, the same thing repeated. So what I'm going to do is work on those. And the first rule was change the connective even. I keep saying collective. Anyway, there you go. All I've done is changed the connective between the two. I've changed the or into an and. It's the first thing. Working only in the brackets, I'm ignoring everything else. The second rule then said, change the individual variable. Remember, we're still only working with the same section. You don't suddenly expand into a new view. We're only dealing with C and D in this case, so we simply change their individuals. The knots have become not knots. We haven't touched A and B, haven't touched anything else. We're only dealing with inside the brackets. And the last part was change the entire expression. And if that confused you, all I mean is swap. So then C and D is knotted. This is now a NAND. And knotted is a NAND. And knotted is a NAND. So we've actually got two of the NANDs that we're looking for in the first place. So we seem to be on the right path. Okay, so let's have a look at that again. That's what we ended up with. Mathematically, you might sit there and say, okay, now what do I do? Do I treat this as one expression? But actually, again, if you look at this mathematically, you should be able to see that if I treated this like a plus in mathematics, then actually I've got two of the same expressions there. And therefore I can apply simple mathematics, bring that outside the brackets, and treat the and as a multiplication. Because in a way, that's what it is. So if I take the C and D outside, I've now got A or B. If I multiplied A, or if I, ANDed A with C and D knotted, then I would end up with that expression. I'd have to do the same to B, and I'd end up, so I can go back from here to here if I wanted to. But that's really helpful, because now I've got an expression in brackets where I can do the same thing. I can change the connective from an or to an and. I can change the individual sign from a not to a not. And I can then change the entire expression to there. I've dropped the brackets because just like in mathematics, if everything's being multiplied, there's no point in putting brackets around it. It doesn't change the result. I've got one NAND there, one NAND there, and I've got an AND there. Now the question said using 4 NAND gates. That's what we've ended up with. But it did distinctly say 4 NAND gates. So how are we going to get 4 NAND gates from this? Well, actually, the answer is relatively simple. That's the solution. The trick here is to remember that a NAND gate needs 2 inputs to be 1 to give a 1 at the end, but then be knotted so it gives a 0. So as long as these inputs are the same, then all this is going to act like is an inverter. This is a NOT gate using a NAND gate as a NOT gate. There's my CD NAND. There's my AB NAND. This NAND's the result, and this simply inverts it. And if I invert an inversion, I get back to what I should have had, which is NAND. This is simply undoing that. Just to confirm. That's what we started with, yes? 3 1s are 0, 3 1s are 0, 3 1s are 0, 4 zeros. That's what we've ended up with. That's what we had originally. And if we compare the two, we can see that we've got exactly the same result. So our system is solved. Just to make sure of that, that's what we started with. And that's what we ended up with. So why? Why bother going through that? Well, several reasons. We've ended up with a simplified system. Yes, that's easier to understand than this. This only requires one of the 4000 series chips, the one with 4 NAND gates on it. This requires a NOT chip. It requires one OR chip, and would require one AND chip. We'd also wouldn't be using 2 of the ANDs or 1 of the ORs. Here we're using the whole chip. So cost effectively, I'm buying 1 chip for the price of 3. So cost is a benefit from using De Morgan's. I only need to use the same gates, therefore I can use 1 chip with 4 of the gates on there. Complexity, obviously, that's far more complex than this. Equally think about the fact that if this has got 3 chips, the amount of wiring I've got to do to go from one chip to the next, the amount of space I'm going to have on my motherboard to cater for those 3. Now I only need 1 chip and a little bit of wiring going between the legs. So complexity is solved. And if that's not convinced you that actually following De Morgan's a good method, then the other way of looking at it is that each one of these slows down the electricity. Each one of these takes time to process. So for each time it meets one of these, you're slowing down the result. It takes time to get from here to here. So if I go through here, the process is a lot faster. 1, 2, 3, 4, going through each chip, plus each of the processes here is much faster processed here. So speed, cost, complexity. Okay. So now let's look at another addition to this system. Boolean is simply looking at truth or false. Zeros, ones, yeses, nos. That's all Boolean is interested in. Everything you know about binary, Boolean is interested in. Boolean is simply the representation of zeros and ones. And there are certain things that we can spot when we're talking about logic gates, when we start looking at those logic decisions. For example, let's have a look at the situation where I've got A ANDed with A. According to the minimalization system, A ANDed with A is exactly the same as saying A, so why bother with the AND? Replace it with A. If we look at the circuit, that's actually what it means. It simply means taking the 2 inputs. I've only got 1 input, A. Therefore, it's doing this, it's joining 2 up. Now when A is 0, my output can only be 0. It can't be anything else. And if my A is 1, again, the output's exactly the same. So there is no point in this circuit in actually having the AND. You might as well simply run a wire straight across. So you lose. If you ever come across this, you can reduce it to simply that. Nice and simple. A and not A. Well, as we know, knotting something inverts it, therefore, whatever A is, not A is going to be the complete opposite. And since an AND gate needs both of them to be 1, and there will never be an occasion where both of them can be 1, because the one is the exact opposite of the other, then whenever A is 1, not A, by the way, that's a simple way of showing not A, is not the line above, that's just a quick diagrammatical way, is 0. Therefore the result is always 0. So A ANDed with not A is always 0. So if you find it in an expression, you can remove that instantly to reduce down the expression. What if I've gone 0? Fixed. That means no electricity is being supplied to that leg of the chip. Well, quite simply, the AND gate needs a 1. It needs 2 1s to accept a 1 at the end. So if I've got the 0 there, instantly I can decide it's no use to me. I'm always going to have 0 coming out of the end. What if I have a 1 attached to it? Well, then actually, I don't care about that. The only decision that's going to make this change is the condition of A. This is exactly, well, it's not exactly the same as this, but it comes out with the same result. This AND gate is only concerned then with what condition A is. So if you've got A ANDed with 1, you might as well just have A. They're the ands. And you need to know those. But they don't need to memorize those because they're pretty logical. And that's the key thing behind Boolean, is logical. That's the beauty of it. It makes absolute sense. Here's the ORs. ORs only are interested in one of the inputs being 1. So as long as I've only got one input being 1, then I'm going to get a 1 coming out. So if my input is set to 1, then I don't care what A is doing at all. A can go 0, 1, 0, 1, 0, 0, 0. I really don't care what it does because I've got the 1 I need. Therefore, an A ORed with 1 is always going to give me 1, and so drop it out of any expression. Same with 0 in the inverse. Since I need a 1, that line with 0 doesn't count for anything. It might as well not be there. I might as well not bother. The only thing that's going to change the state of my output is my input from A. Therefore, A ORed with 0 is only ever going to be A. So again, drop the OR. Get rid of the 0. Once again, if I only have one input, my output can only depend upon that one input. So again, don't bother with the process. Reduce the need for that gate. Reduce the need for that chip to be involved. Drop it, replace it with a simple wire going straight across. And last but no way least, A or not A. Well again, remember in this case, not A is always the inverse of A. So whatever A is, if A is 0, then not A is always going to be 1. And if not A is 0, then A is always going to be 1. So the input of one of those legs is always going to be 1, and therefore A ORed with not A is always going to result in 1. So there's no point in having it. They're quite nice. 8 simple little rules. Logic dictates. So let's have a look at an example. The first thing to notice here is that we've actually got A ORed with A and B. But actually what we've got from a mathematical term is 2 A's. A, in this case, is being ANDed with, well, the only thing that can give me A is 1. And this is being ANDed with B. So what I can do is take A and put it inside outside some brackets, recognizing that I'm actually ANDing this with 1. And as we know from our Boolean expressions, that if I've got B and I'm ORing it with 1, then as long as I've got one leg giving me 1, I don't care. The B can be whatever it wants to be, and therefore 1 plus B is nothing more, 1 plus B. 1 ORed with B is always going to give me 1. And A ANDed with a 1 is A. So I can take an expression like this and actually prove to myself I've only got I only need one input. There's no point in having a second input. The gate's lost, 2 gates are lost. All I needed was that one input. The output is exactly the same. Next one's slightly different. In this case I've got A and A or B. I've got 2 A's, but it's a little bit more confusing. So what I'm going to do is I'm actually going to multiply those through. I'm going to AND A with A, I'm going to AND A with B, so I get rid of the brackets, so I'm reversing the brackets. The interesting thing here is that I've got A, and I know that A ANDed with A is simply A. And those of you that are still with me might notice that that is that. Therefore, the rules are the same. So from everything we've looked at at the very beginning at simply deciding on logic. We looked at ands, ors, nands, nors, XORs, XNORs, NOTs. We've looked at De Morgan's theorem. We looked at Boolean expressions. We've then been able to simplify. Those are the kind of things that you're going to come across. Hopefully, that's helped. Alright?